So you have to go to Artus and download this instruction set document. Also, if for some reason you haven't done the last lab yet, you can also download this MCU microcontroller circuit file. But you should have done all the labs, and if you have done lab 9, then you can use your own microcontroller. This MCU is the same file that you did in lab 9, so you don't have to download it. You can use your own microcontroller, and it would actually be even better if you used your own microcontroller, not this file. I only put it here because maybe somebody hasn't done the last lab for some reason, then you can download this file. But you need to use this instruction set. So I have downloaded it. And basically this instruction set is a small Excel file which describes all instructions that our microcontroller can do, and also how these instructions are encoded in machine code. So this page, this is ID signals. These are from lab number 8, I guess, for instruction decoder. Quick reference is very condensed, and the full instruction set full reference explains each instruction that our controller can do. They're all grouped, and they have even some example to write in machine code. So in the chat, you can write if you have done lab number 9 in full. Please do it now. Write in the chat if you have done it or if you have not done it yet, so that I can understand, how much I need to explain to you. The only exception in our file is that our microcontroller does not yet support instructions push, pop, call, and return, because we haven't really developed our understanding yet to implement them. But we will reach it by the end of this lesson, I think. Okay. So some are honest and say that they have not done the lab 9 yet. Some say that they have done it. Well, fine. Those of you who have not done it, download this MCU version 1.0 file to your computer and open it in Logisim. And you should see this. The circuit should look like this. Okay. Maybe its name will be something like video lecture project.circ. So download it now and open in Logisim. And once you have done it, please write in the chat that you have done it. Okay, so open this and also open this instruction set Excel file. So you go to Artus, click on this file, and it says some stupid things here, but I think, let's see, maybe I can, it's interesting. It does not allow me to download. Maybe I have to go into settings and change something. Let's see. Maybe it's possible to enforce it to be downloaded instead of opened. No outcomes. Good. Okay, now I set it to force download. So now when you go to this mcu.circ, this MCU version 1.0, it should force your browser to download the file. And now you can save it somewhere in downloads folder or on desktop. And then after you save it, you can open Logisim, file, open, and select that file. Okay. And the instruction set Excel file is also the second file that you need to use. Can you do it now?
Sorry, I just came. What should we do again?
Go to Artus, scroll down to MCU Programming 1980s, download the MCU file and instruction set file, open this MCU in Logisim and this instruction set in Excel or OpenOffice or whatever Excel file you can use.
Okay, thanks.
Mm-hmm. Yeah. Okay, I need to take a parcel, so you can open it. I'll be back in 1 second. And the last program that you need is either Notepad or Notepad++. I'll be using Notepad++ because it has line numbering. And it will be a little bit easier to write the code. First of all, let's talk about assembly programming. So to write a code on assembly language, basically you need to know what instructions are supported by your CPU. And the programming way is the following. Assembly code is written in, something like in columns, and each line is just one instruction. And usually one line converts to one instruction in CPU. So it's very, very basic, low level. It's simple, but it's not easy. So writing assembly code happens in the following way. So first you type label. And what is label? We will talk about it a little bit later. Then you write instruction name. And usually there is an 8-space tab stop. So I'll write it shortly, instruction, instr, like this. Then you type arguments or operands. And finally, after semicolon, you type comment. So in assembly language, let's see, maybe I can even set view language to assembly. This is the way the code looks like. I don't know if I can set the font bigger. Can you read the text that I type here? You can write it in the chat. Or are the letters too small? So generally, the assembly language looks like this. Label, which is line name, and instruction, operands, and comment. Let's see. Can I set under view maybe? Always on top. Okay. Let's see. Increase font size. Maybe here. Okay, maybe I'll search it in the Google. Notepad++ increase. Maybe I can use, oh, okay, I can use this control plus scrolling. Can you read the text now? Yes, I did this Zoom, I guess. Okay, so this is how the assembly code looks like. Label, instruction, operands, and comment. Most lines don't have a label, so I just leave it empty. And then I type the instruction, for example, add, jump, branch, something like that. And then I type the operands. Maybe it's registers, maybe it's a constant, maybe it's an address. So let's just start writing some code and then we will figure it out. So first thing that basically what we're going to do today is we will write a code which multiplies two numbers. So our processor does not have multiplication instruction. We cannot multiply, but if you have any kind of logic thinking, you know that we can substitute multiplication with repeated addition. So if I want to multiply A times B, I just count, I add A to itself B times, right? So for example, I don't know, 2 times 3, I don't have multiplication in my CPU, but it's the same as 2 plus 2 plus 2, which is basically addition 3 times, right? 6. So we can express more complicated functions with some simpler functions, with some basic functions. So if CPU has addition and subtraction, you actually can do any other mathematic function as well. I can even prove it to you if you have ever studied something called Taylor series. Then you know that any complicated function can be expressed as a sum of function derivative divided by factorial times x minus a plus second derivative divided by a factorial of 2 times x minus a squared and so on. So, and as you can see, something like 1 divided by 1 minus x can be expressed like this. Then also, let's see, e to the power of x can be expressed like this infinite series and so on. So we don't have to have exponentiation function, for example, e to the power of x. We can just express it with x divided by 0 factorial plus x squared to the power of 1 divided by 1 factorial plus x squared divided by 2 factorial and so on. But squaring is just multiplication with itself, and factorial is also multiplication, but multiplication can be expressed as sum. So we can do all of this if we can teach our microcontroller to, for example, multiply. So what we're going to do as an exercise today is we will write some assembly code which multiplies two numbers by repeated addition. So first, I will write it in C programming language. Maybe it will be easier for you, or something like pseudo C. So, and also we will learn to write this code in such a way that we input arguments in random access memory. So I will write some description of the code first. So take A from RAM address number 1 or number 0. Actually, I write it as a command. Take and capital A from RAM address number 0. Next instruction will be take B from RAM address number 1. Then next part is calculate A times B. Then store result in RAM address number 2, for example. Okay, and let's write some C pseudocode. So how do we multiply two numbers using assembly language, only using additions or subtractions or something like that? So what we will do is we will do it like this. Register number 0 equals A. Register number 1 equals B. And register number 3 will be result. So initially, we have to set R3 equals to 0 so that result is empty, right? Then we will calculate for, I will write it like this, R1 equals B, R1 greater than 0, R1 minus minus R3 plus equal to, or I'll write something like this, R3 equals R3 plus R0 and basically that's the algorithm. So I don't know, if B is, for example, 3, then we count from 3 to 0, and while the result is greater than 0, we add number A to the result, right? Is this code clear to everyone? This simple few lines, you can write it in the chat. And then we store the result. Okay, so very simple, right? But here's a little problem. I take calculator, for example, calculator, programmer, and I will enter two largest 8-bit numbers because our CPU is 8-bit. So CPU is 8-bit, which means the largest number is 255 in decimal. We will multiply it with another largest 8-bit number, 255, and what you will see is result in multiplication is, instead of 8 bits, it's 16 bits. And actually in mathematics, you can prove that if you multiply n-bit number with m-bit number, then the result will be n plus m bits wide. For example, 16 bits times 8 bits will be 24 bits. 16 bits times 16 bits is going to be 32 bits, and so on. Two 32-bit numbers multiplied with each other, the largest number that you can get is 64 bits. Okay, so the correct thing to do would be to understand that 8 bits times 8 bits is 16 bits, and the result should be in 2 bytes, in 2 addresses. Store result in RAM address number 2, number 3. In address pairs are usually glued together with column. So address number 2, number 3. And also result will be stretched along 2 8-bit numbers. Okay, so actually R3, R4 will be result. So R3 equals R4 equals 0. And R3 is R3 plus R0. And if you maybe remember from our lessons long time ago, if you add two numbers and you get overflow, then by doing add with carry, you can add this overflow to a higher byte. So R4 is equal to carry plus 0. I'll just show you it with an example in Paint. So let's say we're adding two 16-bit numbers. First bits will be 0 to have an easier result. This is 1. And the next bits will be, I don't know, whatever. So let's say we have this. This will be result. And it has been counted to this big number. And then we add, for example, 255, which is all ones. On 8-bit system, if we add an 8-bit number with 16-bit number, we first add bottom parts. So 0 plus 1 is 1, 0 plus 1 is 1. here's 1, 1, 1, 1, 1, and here 1 plus 1 is 10, but this overflow is stored in status register. So bottom part we add with add. But to enforce this overflow bit, which is inside the carry of status register, we do add with carry to the top part, and we just add all zeros. And in that case, we force the CPU to add this overflow carry to top part. 1 plus 1 plus 0 is 10. Okay, this is why we made this add with carry to our CPU, so we can add 8-bit numbers and somehow magically, with some trick, add also 16-bit numbers, for example. So let's test if I calculated everything in this calculator. So programmer, this first number is, so here is the middle. This number is in binary 1, 1, like this, plus all 8 ones, and the result 1, 0, 0, and then 7 ones. Okay, so what we just have to remember is we first add bottom parts with add, and then top parts with add with carry, ADC. And since it's 16 bits plus 8 bits, 8-bit top part is just all zeros, which we can store in some register R5, and then we add, for example, bottom part with bottom part, and then top part with, for example, R5 equals 0. We'll just write 0 to it, and add with carry. So let's try to write it with the code. So to add R4 is carry plus 0, we need to have 0 somewhere. So we will be using register R5 equals 0 for top part carry addition. So this is something like a temporary register. So R3, R4 will be result. It will become different than 0, but this R5 we'll use as 0 all the time. So our code now looks something like this. R1 is B, R1 greater than 0, R1 minus minus. R3 bottom part will be R3 plus R0, and R4, which is results top part, is just it plus carry. Sometimes carry will be 0, so nothing will be added. Sometimes carry will be 1, and 1 will be added. You will see it in the code. So, and also what I have to mention to you right now is something called endianness. Endianness. So endianness is a term which is used to decide whether we store top part of the number in higher register and the bottom part in lower register, or the opposite way. Bottom part is in higher address or higher register, and top part is in lower register. Actually, humans, when we read from left to right, we normally count from left to right, 0, 1, 2, 3, 4, and so on. And we will also naturally write higher part of the number in top address. In this case, it will be 0x01, and the bottom part will be in higher address. So 1000 is 0x80. However, in the microcontrollers, usually bottom part is in lower address. So basically both ways are correct. There's nothing wrong with using either one. If you put bigger part in lower address, it is called big endian because bigger part is first. And if you do it the opposite way, if you store bottom part in lower address and top part in higher address, it's called a little endian because a little is first and big part, the heavier part, higher part is only following. So in desktop computers, the system is usually big endian historically, but microcontrollers usually use little endian, and I think that ARM processors are by standard big endian, little endian. So in microcontrollers, bottom part lower address, top part higher address. In desktop machines, usually the opposite way. When you start, if you have to work with certain machine for a longer time, you'll just memorize it from your head. But okay, so as you can see, big endian is the dominant ordering also in network protocols. So in networking, there is this something called network order, which is actually big endian order. So if you want to send a 16-bit number over Ethernet, you'll write top part first, higher part first, lower part last. This is called network order. But in microcontrollers, little endianness is the dominant ordering process for processor architectures, ARM implementation, RISC-V implementation, and so on. So sometimes when you work with microcontroller and need to send something over the network, you have to manually use some code which swaps the bytes around in the opposite order. But anyway, in microcontrollers, it's usually little endian, so we will be using little endian. And in that case, so using little endian. So in that case, it just means that bottom part will be in R3 and top part R4, and top part will be in address number 3 and bottom part in address number 2. And oftentimes it's written in this way: address number 3, number 2. It's like top part in 3 and bottom part in 2. That's just how it's written. Okay, let's start programming. Okay, so first thing that we need to do is read the numbers from random access memory. So in my CPU, for example, in random access memory, I will manually write numbers, for example, 4 and 5. 4 times 5 will be 20. So in address number 0, I write 4. Address number 1, I write 5. Now let's go to our instruction set and check out which instruction reads number from random access memory. Actually, let's first go through all of our instructions. So first instructions are arithmetic logic unit instructions: add with carry, increment, decrement, negate, subtract with carry, move, and or XOR not, logical shift left, logical shift right, rotate left, rotate right. Okay, next instructions are compare. So they subtract one register from another and set flags, but they don't store the result. We'll be using it later. Next is LDI instruction. LDI instruction loads a number into a register. For example, we will write LDI R3 0, which is just, you know, setting a value to register. And here, LDR instructions are the ones that load value from RAM. So they copy value located in address A to register RD. And we write it as LDR, for example, R212. It means take value from random access memory location number 12 and copy it into register R2. So let's just try to do it. In our case, number A is located in random access memory address number 0, and we will use R0, register 0, to store A. So the line will be very simple. LDR, load from RAM, into register R0 from address number 0. So I'll write it like this. Copy value from RAM. Actually, we'll be using the word load instead of copy because it's historically the way how it's written. Load, and you'll also read load in documentations of other CPUs. So I'll just use it the same. Load value from RAM address 0 into register 0. You know, stupid way to write, but that's how it is. Okay, that's the first line. Next, we want to copy B to register R1. So I'll type the same way, LDR, load from RAM. First, and historically, it has been written in this way. The first argument is actually the one into which you copy the result. This is why it's in this order. So R1, 1. So in some assemblies, we write hashtags in front, like saying this is address, not just some number, but address. But since we are loading, we don't have to do it. It's just a way to type it. When you learn a new assembly language, you just check out how addresses are written, and that's all. So LDR register 1 from location 1. Load value from RAM address 1 into register 1. Okay. Next thing that we need to do is we need to initialize the result to 0. Maybe there are some random numbers inside the registers, maybe some old values or something like that. So we need to set R3 equals 0 and R4 equals 0. And actually, let's check it out, how we can do it. Simplest way, LDI, load immediate, register R3, 0. So it's just historic name of this instruction, load immediate. So immediate means a number, basically. So LDI or load immediate means set register equal to some value. However, for your education, there are other implementations of setting register equal to 0. In some assembly, you will have an instruction called clear register. For example, R4. We also need R4 equal to 0 because it's the top part of the result. And clear instruction is often implemented as XOR R4 with itself. Because if you think about it, it's possible that clearing register by XORing it with itself in 32-bit systems where instruction is 32 bits, sometimes values are stored in some flash memory and they're copied from flash to register. So to save some time, some space, yes, you can also use LDI R40, but I'll just explain to you why oftentimes microcontrollers implement register clearing as XOR with itself. So in 32-bit ARM processors, instruction is 32 bits, and registers are also 32 bits. So obviously, if you want to load a number, a 32-bit number to a 32-bit register, and instruction is only 32 bits, it will be obvious that a 32-bit number does not fit inside the instruction because some bits are used as the instruction tag, you know, that it's LDI instruction. So in systems where number is the same size as instruction, usually number is stored in the next instruction, and program counter jumps +2. Okay, so oftentimes when you want to load a large number into a register, large number is stored in as the next instruction, and this first instruction says copy next instruction into register and jump by 2 instructions, you know, like skip this line, and it takes 1 extra instruction and also makes the CPU more complicated. So oftentimes, if you want to load register equal to 0, on bigger systems, it's not so good to load 0 into register. It's better to clear it, because clearing is mathematical operation. It always fits in 1 instruction. So oftentimes in bigger systems, clearing a register is performed using XOR R4 with itself. Check it out. What happens if we XOR a number with itself? 1 0 1 0 XOR'd with 1 0 1 0. 0 XOR 0 is 0. 1 XOR 1 also 0. So XORing register with itself clears it, clears the register. Okay. Also, another option would be, for example, and obviously another way to clear a register is subtract a register from itself. Sub R5, R5, right? Understand? So we can clear register to 0 in 3 ways. In our system, we could have used LDI in all 3 cases, but in larger systems, it might be better to clear register to 0 by some kind of arithmetic. So for example, XORing register with itself or subtracting register from itself. All 3 ways, we get 0 in the register. Also, we can load R3 equals 0, and then we can also copy R3 into R4 and R5. So, you know, many ways to do it. So now we need to move on. We're not very fast here, but lots of information. So we have set R0 equal A, R1 equal B, and LDI. And here we have cleared the result and this temporary register R5, which we need for top part addition with carry. Now we need to write this loop. So for R1 equals to B, this we have done. R1 greater than 0, R minus minus. So How do we do it? Okay, let's do the classic way. So first, we need to check maybe b is already equal to 0. If b is 0 in the beginning, then we don't have to multiply anything, because anything multiplied by 0 will be 0, and we have cleared the results, so we wouldn't have to do anything. So first we need to do this comparison. And also this is how for loops are calculated by processor. So one time in the very beginning of for loop, this R1 equals to B is done. So it is like done before the loop goes into loop. Then for loop, also in C programming language, first checks this equation, and we can check it with instruction called compare. We need to compare our letter B with 0. Fortunately, 0 is stored in R5, so we can right away compare. So compare CMP R1 with R5. Compare B with 5. With 0. What compare does is it's calculating R1 minus R5, but it doesn't store the result into R1. So it just subtracts. And let's say we have 0 minus 0, the result will be 0. So what we need to do now is write branch. So if subtraction is equal to 0, then we need to jump to the place where we store result in RAM. We have completed the code. So branch if equal Q checks if 0 flag is set. So if we subtract one from the other and they were equal, then 0 flag will be set. But if R1 is greater than 0, then 0 flag will not be set. So BREQ to finish. We will call the end of loop finish. So if R1 is 0, then finish. Yeah, so we compare R1 with 0. But if they are not equal, if R1 is not equal to 0, then let's see, what do we do? Then we need to add R3 plus R0 and R4 plus carry. And it's a little bit easier than you might think. So basically, first we need to add A to the result, R3. So basically add R3, R0. Then, to not miss out on the carry, we need to do add with carry R4, R5. So like this, add A to result, add carry and dummy 0 to top byte of result. Then we need to do this R minus minus. And fortunately, in all processors, we have this arithmetic logic unit instruction dex, decrement. So we decrement R1 So we decrement the multiplier. And actually, if we check out decrement, oh yeah, and then we need to jump to the beginning of the loop. Basically, always we would jump to, for example, this comparison. Once we decrement R1, we need to jump to this comparison where we compare R1 to 0. If it has or hasn't decreased to 0, I'll write it like this: jump to beginning, for example. And now we will name this line begin. So this is how we use the labels, and also it's followed by a column. So we call this beginning of this loop, for example, a label begin, and then we jump to this place in the code where we compare R1 with R5. And let's say B was equal to 1. So we did all of this, decremented B from 1 to 0. We jump to compare. We compare 0 equals to 0. They were equal, so it jumps to finish. So this next line I will call finish. Finish. And once we have completed our multiplication, we need to store the result. So output R3, R4 to RAM. So storing can be done using instruction called str, store to RAM. Store to RAM. And in RAM address number 2, we store the bottom part of result. So R3 we store in RAM address number 2. And store R4 to RAM address number 3. Something like this. And as you remember, all code has to end with end, jump, and so that once we go to the last line, it starts jumping to this line forever instead of going into an initialized flash memory and starting to execute some random instructions. Okay, so all programs, even C programming language programs, automatically append this end jump end to your code hidden from you, so that the code doesn't go into some uninitialized flash part. So let's see, end jump end of program. So is this code easy to understand? All the things that we did here. So if somebody didn't understand some part, you can ask now, because I want you to kind of fully understand how this code works. Okay, it's easy to understand. And actually, there are some CPUs which, okay, so while line 13 is finished. So let's say somebody wrote 0 times 0. We load 0 into register R1, 0, 0 in register R1, then we clear the result, and then we compare our second operator with 0. If it has reached 0, then we jump over all of this code and we store result. So we don't do this. And therefore, this line, in my opinion, is finish. And this is where we jump to once we have done this loop so many times that this B has reached 0. It's like down counting. Okay. Any more questions? Yes, exactly. So loops are made thanks to the labels. Jump jumps to the label that we give it. In reality, it translates to line number, but we will do it a little bit later as the next step in assembly to machine code translation. But yes, jumps jump to labels, and branches also branch to labels if certain condition is met. So branch EQ is if zero flag is set, then jump. So zero flag is set if two numbers were equal or if zero is reached, so then you branch. And so this is like this. Also, one interesting thing, we can actually speed up our program a little bit, because when we do decrement, if R1 reaches zero, zero flag will be set after decrement operation. You can check out it in arithmetic logic unit. So decrement is the destination register -1. It sets zero flag. So if R0 reaches zero, we don't have to compare it with zero, because zero flag will be set after this instruction. So actually, we can move this begin to this place, because decrement already sets zero flag if R1 is equal to zero. So we can do jump to this place. If zero flag is set, then we jump to finish and we exit. Did you understand this trick? Jump instruction does not influence status register. This is why status register is only updated after arithmetic logic unit instructions. So we decrement R1. If it reaches zero, zero flag is already set in status register, so we can jump directly to branch if zero set. So branch if equal has a second name, branch if zero set. It's like the same thing. So we jump to finish. And in this Excel, I don't know if it has been written in this way, but some of these instructions have two names. For example, branch if equal means branch if zero set. Just historically, it's used for equivalence comparisons, so it's named breku, but it just checks for zero. So correct name for this comment will be if zero flag is set in status register. So also in one old programming language called Pascal programming language, all loops began with begin and ended with end. Just historically, end, jump, end is used for end, so I was not using word end because each label can appear in the code only once, so that jump knows to which label to jump. If you have two begins, how does this jump know to which begin to jump? So labels can only appear once, right? And therefore we have this begin and finish. Okay, if you understood this code, then let's go ahead and do the following things. We will be doing now assembly, how a computer does it. So first thing that it does is it replaces labels with line number. Because program counter does not recognize names, because it's just stupid counter, we actually replace label names with line numbers counting from zero. So if this is line number 0, it will also be instruction number 0 in flash memory. It will be located in flash address number 0. This line will be located in address number 1, number 2, 3, 4, 5, and 6. So begin is equal to 6. and jump will actually translate to jump to line number 6. I'll write begin in brackets, or maybe as a comment without this red. So this is line 6. So here I have an offset of 2. So begin is line 6, 7, 8, 9, 10, 11. So finish is actually 11. So I write 11. Okay, then I'll write it like this. And end, so finish is 11, 12, 13. So end is actually 13. So labels translate to line numbers because computer can only perform code on numbers. You know, it's 16-bit instruction. It doesn't understand text. Okay, so first step was we replaced labels with line numbers in which the label is located. Okay, so next step is translating each line into assembly, into machine code. In our CPU, it will actually be done quite easily because the first 4 bits are instruction name, next bits is the register, then it's either a number or something like that. So it will be actually easy. So for that, we can use this instruction set quick reference. And we can find that, for example, LDR translates to 0011. Where can I write it? I'll write it, for example, here, 0011. Next 4 bits is destination register. So register number 0 is obviously just zeros. And then it's the address of RAM. So address number 0 is just all zeros. And we can also write it in hex because Logisim, when we go to Logisim and select edit contents, we type in values in hexadecimal format. So I have to translate it to hex, but hex translates 4 bits into one symbol. So 0011 is hexadecimal 3, and these just translate to zeros. And we can either write 0x and then hexadecimal number, or the number in hex and then h at the end. I'll do it this way, so it's a little bit shorter. Next instruction is LDR R1 1. So again, in this quick reference table, I find LDR, it's 0011. Then register is number 1, so 0001. Then address is 1, 00000001. And in hex, it's 3101 H. 3101. Next is LDI R30. LDI is 0010, first 4 bits, 0010. Next bits is the register. Register is register number 3. 3 in binary is 0011. And then is the number K, 8-bit number. So it's 0, so it's 00000000. And in hex, it is, let's say this is 2300H. And these numbers we will give CPU, and it will be able to decode everything because it's made in this way. Next is XOR. For arithmetic logic unit instructions, it's a little bit different, this ordering of bits. For mathematical and logic instructions, first 4 bits are always 0. 0, 0, 0, 0. Then it's the first register, register 4. So 4 is 0, 1, 0, 0. Then is the operation XOR, which in hexadecimal is A, in binary is 10, 10. And then the second operand, R4. R4 is 4, 0, 1, 0, 0, equals 2, 0, 4, A, 4, H. Okay, so in our CPU arithmetic logic unit, this name kind of goes between the operands. So the beginning is all zeros, then is one number, then is operation, and then is the second number. Subtract is also arithmetic logic unit operation. Register number 1 is 5. 5 is 0, 1, 0, 1. Then subtract is also 5. It's the operation number 5 on our CPU 0, 1, 0, 1. And second register is 5, 0, 1, 0, 1. Okay, so in hex it is 0, 5, 5, 5, H. But you know, it's just coincidence. Okay, next is compare. I'll write it a little bit shorter, so we don't have new line. Compare instruction. So compare is here. And actually, I didn't tell you, maybe we'll do it as an exercise. So when we do comparison, we need 2 registers. So if, for example, I wanted to compare R1 to some different number, for example, 100, I would first need to load 100 into the second register, and then I compare them to each other. However, if I need to compare a register to 0, there's a smarter way to do it with just one register. Actually, multiple smarter ways. Check it out. First of all, what happens if we do OR on register itself? So register number value is, for example, 0, 0, 0, 1. If we OR it with itself, we can do it even as an arithmetic logic unit operation. If we OR number with itself, we get the same number. 1 or 1 is 1, 0 or 0 is 0, but flags are set after every arithmetic logic unit operation. So if the result was 0, 0 flag would have been set. So if we do 0 or 0, we get 0, and also 0 flag is set equal to 1. So if we need to compare a number with 0, then we can just OR it with itself. The result will not change. The number ORed with itself is the same number. But if the number is 0, result will also be 0, and 0 flag will be set. So we can do comparison a little bit better by OR R1 with itself. Compare B with 0 by ORing it with itself. If 0, the flag will be set. Understand there? And to be honest with you, we can also AND the number with itself. ANDing number with itself yields the same number. If the number is 0, result will be 0, and 0 flag will be set. So we can either AND the number with itself or OR the number with itself to compare it with 0, like intrinsically. And it just will be a little bit shorter way. Then we don't need a second register which holds zeros. So in our case, R5 is necessary for addition, but for testing for 0, it isn't. And actually, in some processors, this operation is called TST. TST instruction. For example, R1. It looks like a different instruction, test R1, test, and its explanation is test for 0, but actually what it translates to is OR register with itself. So to see if it's 0. Okay, let's do it this way. It's smarter and you need to learn something. So compare B with 0 by ORing it with itself. If 0, Z flag will be set. Let's translate it to machine code. So OR is arithmetic logic unit instruction. It starts with 0. First register is 1. Actually, this we can write in hex already in our heads, because arithmetic logic unit always starts with 1. First register is register 1. OR is instruction number 9. So it will be 9. And second register is 1. So in hex, it will actually be 0191 in hex. I don't think we need to expand it to this binary format. Okay, let's move on. Branch if equal to line number 11. So branch if equal, let's scroll down to our quick reference guide to branch. Branch always begins with 0110. 0110. Next is condition bits, and equal is 5. So in our CPU, it will actually be like 0101. Okay, maybe I cannot type it here. 5 is 0101, which basically compares 1 to flag number 1, which is 0 flag. So it's 0101 like this. And then last 8 bits are address to which to jump. Address 11. I don't know how it is in binary, so I'll use this calculator. In decimal, it's 11. In binary is 00001011. Oops. Like this, I guess, yeah. Equal to 0110 is 6. I just remember it from my head. Is 6. 0110 is 6. 0101 is 5. 000 is 0. And 1011 decimal 11 hex, it's B. So it should be something like this. Okay, next is add. Add is arithmetic logic unit instruction. So it's 4 zeros. Then it's first operand, which is register R3. So it's 3, it's 0011. Then add, in our quick reference, add is operation number 0. And R0 is 0. Equal to 0300H. Next is add with carry. Beginning is all zeros. Then 4 is 0100. Add with carry is instruction number 1. So it's sub instruction number 1, 0001. And R5 is 0101. Equal to 0415H. Actually, maybe it's even easier to write it in hex directly, because it kind of breaks into 4 nibbles, so maybe it's easier to write in hex. Can we try to write it in hex directly? Decrement R1, that is here, it's number 3. So let's try to write it in hex directly. Arithmetic logic unit, first 4 bits are always 0, so it's just 0. Then register number 1 is just 1. Decrement is operation sub operation number 3, and the second operand is not used, so it can be 0, H. Then jump to line number 6. Line number 6. In hex, jump is 0101, which is 5, so I can just type 5. Then next 4 bits are not used, they're just 0. And the last 8 bits is the address to which to jump. 6 in hex is 06, like this. So I could write it immediately in hex. Okay, next is store. Store is 0100, which is 4. Then it's register, from which we take the number. It's register number 3. Okay, so if we're looking at this Notepad++, it starts numbering from 1. It should have started 0 at 2. Therefore, this is the reason why we have this offset, because we should only count from the beginning of our first instruction. So this is instruction 0. This is instruction 1, 2, 3, 4, 5, 6. So begin is actually at 6. Okay, storing. Store is 4, register number 3 is 3, and address in RAM is 2, so it's 02 in hexadecimal. And store R5, 3. Again, storing is 4, register R4 is 4, address 03. H. And end, jump end is 5, then it's 0, and line number 13 in hex is D, so it's 0D. I think that we have completed this translation. Did you understand how we translated the lines of assembly to machine code? Okay, I hope you understood. You know, it is a lot of information in your face, right? But actually, our CPU is pretty easy. In other CPUs, oftentimes, these bits do not translate beautifully into 4 nibbles, which beautifully translate into single numbers in hex. In some other CPUs, these control bits and register bits are smeared all over 16 or maybe even 32 bits, right? Every time located in different position. So it's much more complicated. This toy CPU that we built in Logisim, I tried to make it as easy and simple and basic as possible. So these bits really translate directly to machine code. First is instruction type, then it's register number 1, then it's operation and register number 2, or register number 1 and then address, or condition and address, you know, so it's simple. Now let's type it all into our Logisim and try to run it and see maybe we have built it correctly, maybe we have built it in the wrong way. So in Logisim, as I mentioned before, in this MPU view, you know, if you open this Logisim, you click MPU 2 times, right? You enter this view. You can, you need to check out that your clock is not bright green, but it's dark green. And you click reset. So it's reset. And you can also clear RAM before you do something. And first, let's input our code into this flash memory, this read-only memory. We right-click and select Edit Contents, and we are in this view where we can enter the instructions. These are very small numbers. Maybe you can hardly see anything, but you know it's there. And then we can also open our Notepad, and I'll put it, for example, here. And then I'll carefully input these hexadecimal instructions into this hex editor. So I click on the first location of this thing, and then I'll type it. So the first instruction is 3000. Next instruction is 3101. If I click tab, it doesn't go to the next. So I have to, maybe I do, okay, I can do it with arrows. So next is 2300. Whoops. Next one is 04A4. Next is 0555. Next is 0191. Next is 650B. 650B. Next is 0300. Next is 0415. Next is okay, 0130, I guess. 5006. 4302. 4403. 500D. I guess, I don't know. So to enter hex editor, you right click on this read-only memory, this program memory, and click edit contents. And then you see this window. And you input values into it. And when you close it, it doesn't delete it. It remembers the values. So let's see, 3. No. Okay, so I have input all of these into my hex editor. And if you want to, you can also input it. So I can kind of pause a little bit and you can type in if you have input these hex values in your computer as well, if you want to. So maybe 1 minute I shut up and you input the values in your Logisim in your computer, so you can also run this code and check if it's working. Okay, so 1 minute is over. Did you copy these values into your Logisim? Okay, some have not. You can do it later. Then let's go to our code. So when I click reset, what happens is all registers are reset to 0, and program counter is also reset to 0. That's the two things that reset signal does. Also, let's remember that I immediately need to input manually some values into random access memory. So in real life, I would use LDI, but because I want to test with various values and I don't want to edit the flash, you know, it's kind of like API. So I'll just insert these numbers in random access memory. Let's say I want to multiply 2 times 3. So first number will be 3, second number will be 2, and so it will be 3 times 2. It will add 3 to 0 2 times. So 0 plus 3 is 3, plus 3 is 6, and it should write 6 here in the result. Also 6, 0, 0, 0, like 16-bit number. So let's see. I click clock 1 time on a rising edge of the clock signal. CPU buffers the instruction. So inside instruction register, it photocopies the incoming instruction and holds it this way all the way until the next rising edge of the clock, so that the instruction doesn't woggle around. Next thing is, because it's LDI instruction, we can see that instruction decoder took this 3 and decoded in such a way that it selects GPR source select 01, which is value from RAM. It enabled write enable to general purpose register because we want to write into general purpose register. It also disabled status register writing because we only want it to be set when we do arithmetic logic unit instructions. It disables jump branch because it's a regular instruction. We just want program counter +1. It disables writing to random access memory, but it enables reading from random access memory. Also, it doesn't force jump. It's a regular instruction, and it selects register A 0000. It's actually the bits in the instruction, but you know, instruction decoder set them correctly. Then flag compare is off, flag select is off, everything else is off because it's RAM to general purpose register. So let's go back to CPU. Inside the general purpose register, we can see that write enable is on. So on falling edge of the clock, value will be written. Also, address for writing is selected register 0. And also, we already have data from random access memory arrived. This is number 3, which is inside the RAM. Of course, in real CPUs, it takes some nanoseconds for this data to go into CPU, but you know, it has already passed. So this number 3 is output on the data line, goes inside the CPU, value from RAM is 3. This multiplexer is selected to 0, 0, 0, 1. So 3 is passed here into general purpose register and is already waiting at the doorstep of R0. So, and for program counter is 0, program counter +1 is 1, and this multiplexer, since it's not a jump function, it has selected that the result of the program counter will be program counter +1, so it will just move to the next instruction as usual. So on falling edge of the clock, all values are written into registers. So on falling edge of the clock, program counter is updated to program counter +1, and general purpose register R0, value is written equal to 3 from random access memory. Okay, on next rising edge of the clock, instruction is photographed in instruction register. Address of RAM is selected, RAM address number 1, value from RAM coming is 2, register for writing selected is register R1, its address for writing, it's the part of our instruction which sets it write enable, great. So on falling edge, program counter moves to the next instruction, and number 2 is written into register R1. So everything works great. Next instructions will clear our registers. For the play, I will, let's see. Oh, we didn't use register R2, but registers R3, R4, and R5 should be set to 0. For a play to prove you the point that these registers will be written to something, they will be cleared. I write some random numbers in them. And let's see, on the rising edge of the clock, instruction decoder receives instruction. It selects write enable general purpose register, and GPR source select is 0, 0. What does it mean? It means that this multiplexer is select to position 0, 0, which feeds bottom 8 bits of instruction to register. So value 0 will be written into register R3. Let's see, on falling edge, it happens. Register R3 is 0. Next instruction for clearing register was XOR R4 with itself. Let's see if it happens. On rising edge, instruction is fed into CPU. And let's go to instruction decoder. In here, instruction decoder says, let's see if I'll compare. I don't know what the fuck that is. Register R1, B, bottom, source select is 1, 0. So the result into this general purpose register comes from input number this. And in arithmetic logic unit, instruction number 6 is selected. So let's go into it. A is selected the value of register R5. B is also the same thing. Operation is 1, 0, 1, 0. Is it correct, or is it in the opposite direction? Let's see. 1, 0, subtract. Oh yeah, XOR is 1, 0, 1, 0. And arithmetic logic unit has already calculated that the result is 0, 0, 0, 0. So these two numbers are XOR'd with itself. The result is 0. 0 is fed into this multiplexer. Register number 4 is selected for writing, and it will be written to 0. Okay. The next option was, of course, subtracting register from itself. So on rising edge, the general purpose register selects for A and B register number 5. It is also selected for writing result. Arithmetic logic unit. So number 5, 5 is fed into A and B. 0, 1, 0, 1 is subtract. So subtraction will be performed. This number minus itself is 0. So result is 0. And CPU view. Okay, so 0 is fed here and the result is 0, and it will be written to 0. On the falling edge of the clock, we can see 0, 0, 0, all is 0. Great. Next instruction is compare, I guess. Or ORing R1 with itself will test for 0. So rising edge, register R1 is selected for A and for B. Its value 2 is fed into A and B channels. Arithmetic logic unit has received them. It has done ORing with itself, so 2 or 2 is 2. But what we're interested in here is status register outputs B and Z, C. So the carry flag is set. I don't know why. Oh, because the old carry flag is fed, is just copied because ORing doesn't update carry flag, so it just set to the old value. Because not all instructions update all flags. And basically, after performing this instruction, status register value is 0, 1, which means that V and ZC, it just means that carry flag is set, but 0 flag is not set. 0 flag is 0, so the result was not 0. And then the branch instruction is performed. If 0 flag is set, jump to line number 11. On rising edge, it copies this instruction. Instruction decoder takes the first 4 bits and selects from them 0, 8 for control signals, which basically say, don't force jump, but enable jump or branch. And flag comparison value is 1, and flag to select is 0, 1, which is flag number 1 counting from 0. So status register value in binary is 0, 0, 0, 1. Flag which is selected for comparison is flag 0, 1, which is the first one, which is equal to 0. Therefore, 0 is fed here compared to 1. They're different. Therefore, result is 0. And program counter will not jump to line number 11. Instead, it will be just incremented by 1. So falling edge. Therefore, it didn't jump to the end. It jumped to the next instruction to be performed. So next instruction is add. Okay, so rising edge, read the instruction. Instruction is address A is 3, address B is 0. So register 3 plus register 0, I guess. Write enable is selected, and in arithmetic logic unit, operation is 0. So 0 plus 3, result will be 3 written in the first register. So on the falling edge, register R3 has incremented from 0 to 3. Then next instruction is add carry. Well, carry was 0, so nothing was added to register R4. And then decrement register R1. So it's selected for writing. Arithmetic logic unit receives 2. 0, 0, 1, 1 is decrement, so 2 is decremented to 1. And on falling edge, register R1 is decremented from 2 to 1. Here it is. And after this operation, also status register was updated, but it's still 0, 0, 0, 1. So 0 flag is not set. Carry flag is set from a long time ago. So it jumps to, so 5006 means jump. So jumping means force jump bit in instruction decoder, enable jump branch, and force jump. So basically, this thing says copy bottom 8 bits from instruction word to program counter. So program counter value is 10, but the new value will be 6. So on falling edge, it jumps to instruction number 6. And this is the reason why instruction register is buffering this thing, because if it jumped to 6, then we would have some problems here. But since it jumped back, but only on rising edge, new instruction is fetched, nothing bad happens. So maybe I speed it up a little bit because we're running out of time. So branch didn't happen. We add bottom part to register R3. So there was 3 added, result is 6. Then top part is bottom part was carry. And then we decrement R1. So register R3, sorry, register R1 is 1. We do the rising edge. Arithmetic logic unit receives 1. Subtracts 1 minus 1, which is decrement. Result is 0. And because all bits are 0, 0 flag is set in status register. This one is equal to 1, the second from the right. And therefore, on falling edge, status register changed its value to 3, which is 0, 0, 1, 1. Then we jump back to this branch. And on rising edge, let's check out. So 0011 is set. This flag number 1, which is 0 flag, is compared to 1. Since they are equal, the result is 1, and it's fed to this multiplexer, which forces program counter, instead of being 7, to jump to line number 11. Because flags were equal to what we compared to, this forces program counter, instead of incrementing, to jump all the way to 11. So on the falling edge, program counter jumped from this to this place. And these are the store instructions. 6 was stored in address number 2, and 00 stored in address number 3, and 500D is jump and jump. As you can see, I can jump as many times as I want. The instruction says program counter force jump bit is 1, and therefore program counter, instead of 13 plus 1, 14, instead of moving ahead, its value is forced to 13 all the time. And this is the reason why program counter doesn't enter some uninitialized instruction territory. Okay, so I guess 3 times 2 is 6. You know, it's successful. Now let's also try, because I want to show you how you can test your code. Let's say you want to test 2 big numbers multiplied with each other. I don't know, 100 times 100, right? It's 100 times 100, 10,000. 100 times 100. Both numbers are smaller than 255. So results should fit in 16 bits. So 100, I guess 100 is 64 in hex. So I'll type 64 here and 64 here. Then, okay, I can also clear RAM to clear old value. Here I type 64 in hexadecimal, 64 in hexadecimal. This is 100 and 100. I can also reset the CPU. Just make sure the clock is off when you reset. And if I want to do this multiplication, I can click this thing 100 times, and I'll click them so many times that my finger will become shorter because of this all clicking, and you know, the finger will be tired. Let's see how far I have gone. So 64, 5e is 94. So I have done only 6 loops. This thing is already 8, and R4 is 02. So I had overflow already 2 times. But in this view, you can also click simulate. Tick frequency, you set it to maximum 4.1 kilohertz, and click simulate. Okay, maybe I'll set it to some like a little bit slower 1 kilo, but you can basically click ticks enabled, and then the clock is automatically operated at the frequency that you selected. Right now I set 1 edge per second, right? And it's slowly doing the code. But if I set tick frequency 4.1 kilohertz, then obviously it does it much faster, and it has already calculated the result. I can see that it's at 500D, which is the instruction. So let's check out if it has calculated the result. So it says that the result is 1027. Let's insert these numbers correctly in calculator, starting from bigger part, hexadecimal 27, and then is 10. And I can see in decimal is 10,000. So I'm assuming that the code calculated everything correctly. Okay, so I hope you understood what we were doing here. And you have a homework. Your homework is here, homework number 1 in assembly programming. Let's make it easier, just one task. So you need to write a faster 8 times 8 equals 16-bit multiplier. Okay. I think I will not tell you what to do. I want you to think for yourselves, but you need to write something that works faster than this naive multiplication. For example, what if we have numbers 1 times 255? Well, it will do addition 255 times. It's slow. Can you figure out from binary arithmetics maybe a faster way to multiply two numbers, right? First, you can try to multiply, for example, 1010 times 1001. Try to figure out what you're doing when you're multiplying on paper, and maybe you can teach the computer to repeat your way of thought in some assembly code, okay? So the homework is write a faster multiplication algorithm. Well, what are you doing when you are multiplying on paper? If this bit is set, you just copy this number, because 1 times this number is just the same number. For the next position, you write 0 at the beginning, which is shifting bits, and then you multiply with the second number. If it's 0, you don't do anything. If it's 1, you copy this number. Then you add 2 zeros and multiply with next number, and then you add 3 zeros, which is shifting by 3, and then 1 times 0 is 0, 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, and so on. And you need to figure out how you can feed this, teach this to a computer using assembly language. Basically, what you're doing is you're shifting and you are copying maybe something, maybe you're not copying, you're checking if this bit is something, so you are doing AND with a mask, so you have to use logical shift. I guess it's to the left. You need to use AND bitwise and add, and add with carry. Okay, so that is your homework. It's not easy, so you start today, and maybe by the end of the week you will have finished. You can also kind of consult with each other if you're too weak to do it on your own, but you know, try to do it. If you figure it out, you will feel very rewarded. And to help you a little bit, I will put this code in Artus, so you know, you can check out this, and then maybe from this you can figure out how to write this other program. Okay.
We will also have a recording of the lecture, right?
One more time, next week?
We will also have a recording of this lecture, right?
Yes, yes, I will put this lecture recording in Artus, and there are also some recordings from previous semesters, so maybe it helps. Save. Okay, so that's all for today. Good luck, and you know, try to figure this thing out. It's actually really simple if you just think. You have only basically 4 instructions: logical shift, and add with carry, to teach a computer to multiply things faster. Okay, so that's all for today, and we see each other next week.